Yeah, so we are going to study, this is chapter 4 again. As I said, the chapter is memory hierarchy. We're going to talk about the locality, which is the principles of locality, and also in terms of different memory, their performance. So when we look at our text, actually the topic also, memory hierarchy. So the first question we are going to ask is, what is a memory hierarchy? So here we say I'll use the term a tile system of computer storage that organizes, let's say, memory levels and based on their speed and also the capacity, amount of data they can hold, and also the cost. So it will be the speed, cost, and the capacity. So the goal again is to provide I'll say the illusion of a large, fast, and inexpensive memory system, which most of the time is impossible. I mean, getting a very large, faster, and inexpensive, not costly. That's the main goal. And I think we have the diagram somewhere here. We'll go back again. So this is how the pyramid look like. So the most fastest and expensive memories are at the top, and the cheapest is at the bottom. So first is registers. Registers also are very small in terms of capacity. Fast because they are very close to the CPU. Even some architecture, as we mentioned in chapter 3, the registers are inside the CPU. So yeah, when a memory is close to the CPU, the fastest time will be less reduced. We are going to reduce the latency period of accessing it. So registers are the most expensive and very small capacity, very small. Then the next will be the cache. And we'll talk about cache in next chapter. And we have at least a major 4 difference of cache based on the number cache 1, 2, 3, etc. Then we have our main memory. Main memory is one of the slowest so CPU normally cannot access. So all this memory are the permanent storage. So I would say storage devices, outboard storage. Normally CPU cannot access data from storage. Data must be loaded to memory. Either main memory, cache, register, then they can be accessed. So when we look at the pyramid, we can say that the slowest or less expensive memory will be the main memory. Main memory. Then we have the magnetic tape, which is again the most cheapest. So let's go back. Yeah. So one of the problems I would say, because our the main goal of a computer designer is to come up with a very good memory that a good memory means the size is very big, a large size, and also easy and actually faster to access, for CPU to access it. And of course, the price is less. So why I mentioned this, we can't do that. That is impossible. But our goal, or our computer designers, architectural, is to balance it. So we need to balance the speed, cost, and capacity. And as we saw it organized in a hierarchy structure, we saw the diagram. Top is fastest and cheap, most expensive, and also small, lesser size also. So the fundamental problem here, I would say that the trade-off. So fast memory technologies are more expensive and have a smaller capacity. Example again is register. Why slower technologies are what? They are cheaper and have much larger capacity. So we saw the memory hierarchy and how it's organized. So that's the problem. Now, solution will be what? Let's use a combination of different memory technologies. The system places small, fast, and expensive memory like cache close to the CPU, and the larger, slower, and cheaper memory like main memory, even hard drive, virtual memory, hard drive card, hard drive further away. So that's the main goal here. And we say to achieve the illusion of a large, so the key word is illusion. Very difficult for this. Large, fast, and cheap memory. Also, as I always said, if you have a question, if you post it in the chat, I can't see it because I'm in a slideshow right now. So if you have a question, I would say the best way to get a quick answer is to speak. If your microphone is not working there, if I hear any noise, like something is dropped, I may check the chat. If not, after the class, during the break time, before break, then we will check also. Yeah, so that's the idea of what is memory hierarchy. Let's wait for a few seconds if it's okay. So again, memory hierarchy is a structural organization of different memory types based on, again, the speed, cost, and capacity. There's now the motivation behind this also is that how will I say? There's a gap. There's a gap, a very large, or I'll say wide gap between CPU speed and also main memory speed. And I think we mentioned this. This is what we call the Van Neumann bottleneck. Processor work very fast. It doesn't have memory. To access memory take time. So this means the processor will stay idle doing nothing, and this will slow the time to perform, or I'll say to increase the performance time of the computer. To complete a task, it may take more time. Yes, and so that's the main goal we want to solve here. So when we say speed, it means what? The fast access for the CPU. When we say cost, of course, cheaper storage. Then when we say capacity, the size, the amount of data it can hold. Yeah. So if no question, so yeah, so this is from the diagram here. So we have registers, which is the fastest and the smallest. The cache can go up to level 3. So some technology also they have, again, level 4. So register fastest and expensive. Cache is next. Main memory, secondary storage, then the tape optical media. Their size are very large and less expensive. So again, that's the diagram here. I think we're going to move on forward unless any question. So magnetic tape or secondary storage devices are most expensive. I mean, I say most cheapest. I would say the largest, their size is more large. Most expensive is the register. The size is small. Yeah. And access time, the speed, very good. So those are the different types of memory. If no question, then let's move on. So next, this is one of the main focus of this chapter, what we call the principles of locality, sometimes referred to as the locality of reference. So I would say locality refers to the predictable patterns in memory access. The goal here is that if CPU access, let's say, memory M1 often, the next chance of accessing M1, since he has accessed it frequently, there's more higher chance that if that memory is free, he can access it again. So that's the whole idea. And here we have two things we have to mention here: the temporal locality and also spatial locality. We know in computer science when we hear the word temporal, it's by go with time. Spatial, of course, we go with space. So those are the two things. In terms of temporal locality, we say that As actually we mentioned it a few seconds ago. Temporary locality means the recent access data is likely again to be accessed again soon. So when CPU access memory some location, the chance of accessing always is higher than the ones. Example will be loops. So loops repeated access the same variable or the same instructions. Then the next one, so this is temporal locality, go with time. And as we said, spatial locality will go with this. So here the data near recently accessed address, of course, is likely to be accessed soon. It's likely to be accessed soon. Example would be like accessing an element of an array sequentially. Yeah, if I go to index 0, next index 1, 2, sequential order. Yeah. So I think that would be a good example because here we say data that are near recently accessed memory is likely to be accessed soon. Yeah. So wait for a few seconds if it's okay. So that's what we are measuring here. So during any interval of time, the program reference memory location on uniformly. And also after, as a function of time, the probability that given a unit of memory is referenced tend to change slowly. So slowly. So the correlation between immediate past and also immediate future memory references patterns is high and also tapers off as the time interval increases also. So again, memory hierarchy works because of the, I would say the fundamental observation about how computer programs behave. And in this case, we are talking about the principles of locality again. So this principle states that again, programs, as we said earlier, tend to access memory locations that are close to those they have already accessed recently. So those are the two types of locality: temporal, based on time, and also we have spatial, which is based on space, location. Oh, let me use the term location, so space. Okay, so if no question, let's move on. No. Okay, so that's what we said earlier. So two forms of locality. We have the temporal locality and spatial locality. So we say first, temporal is about time of access. Spatial is about location or space. So let's wait for a few seconds. If no questions. So that's the same thing we are saying here again. Temporal locality, recently accessed items are likely to be accessed again. The spatial locality, items near recently accessed address are likely to be accessed soon. So it kind of form a cluster of clusters of memory location that frequently be accessed. So locality is the foundation of efficient memory hierarchy design. So let's wait for a few seconds. If no question, let's move on. So next we talk about the characteristics of a memory. This is straight from again, our textbook. So the characteristics of memory first, the access time, the latency. We want to reduce that time. That's the goal. Then we have a cycle time, transfer rate. Transfer rate here, we say the bandwidth will solve it. So if our communication line width is wide enough, more data will be flowing. per the time than if the bandwidth is smaller. Shrink, then data will take long to go. So transferring larger data, preferable need a high bandwidth or longer bandwidth for the data path, or this case we call the bus system. Yeah, the bus system. So access time means the time we need to read or write data. Cycle time will be minimal delay between successive memory, again, operations. Then we have the transfer rate, which is the bandwidth, as we said, rate at which the data can be moved. Then capacity will be the total amount of data the memory can store. Then we have cost per bit. And the cost per bit normally will determine economic feasibility of memory type. Yeah, economic feasibility of memory type. Then we have cost per bit, capacity, and also cost per bit. And we skip the capacity. So capacity, amount of data stored. Capacity before cost per bit. Okay, so the question, let's go. So this is straight from the textbook also. Here we have a table 4.1, which means chapter 4, are the key characteristics of computer memory system. So we can see same as the previous slides, but we have some few things added here also. Location, very important. Normally it's internal. Example will be the processor, registers, cache, or main memory. Then the external one will be optical disk, magnetic disk, and also tapes. Then next we go to the capacity. Wait for a few seconds again if it's okay. So capacity, we can see what they gave to us. Number of words and number of bytes. Then we also have the unit of transfer by word or by block. And then we have the access method. The access method, I think the common one we do even in programming courses is a sequential in order. Okay, so if no question, we go to the performance also. We have the access time, cycle time, transfer. Then we have physical time. And also we have physical characteristics. And then the organization. So let's wait for a few seconds if you have any question. Okay, so if no question, let's keep going. So these are all the possible characteristics of a typical memory system. Also, we have physical characteristics, whether it's volatile, non-volatile, or if it's any of, let's say, read-only memory is erasable or non-erasable. Then organization, yeah, they are using module or memory modules. Okay, so if no question, let's go. So this is and also we'll go details on this. Now, most of the time when we are studying programming language, access will be always sequential, but sequential is not a good way. I mean, it's good, but not very, should I say, very efficient. Yeah. And direct access and random access is what we know a lot. Associative also, this one. So these are all method of accessing data or unit of data here. Yeah. So one thing also we should know that from the user's point of view, the most important characteristics of a memory will be the capacity and performance. This is for users. So 3 performance parameters are used. For example, access time again, memory cycle time, and also transfer rate also. So sequential, I think like a array in order from beginning to the end. So memories are organized in a unit of data called records. Then access must be made in specific linear sequence. They have to be in linear order. So that will be access time. It will be again, the variable access time is variable. Yeah. Direct also will be involved share read write mechanism because individual blocks or records have a unique address based on, again, physical location. And I think the next one, random variable, will be the best. So each addressable location in memory has a unique, also physically wired in addressing mechanism. So let's wait for a few seconds if any question. Now the goal here, as we all say from beginning, is to balance the trade-off between the speed, also the cost, and also again, the size. So here we have to stay trying to balance. And here we talk about the performance and also the capacity. So the 2 most important characteristics of memory are the capacity and also yeah. One thing also with as we said, sequential access, as we said earlier, the memory is organized into what the units of data, in this is called records. And access must be in what? In a specific linear order or linear sequence, let's say. So the store address information normally will be used to separate records, also assist in a retrieval process also. Yeah. Now with the random access, as we said earlier, each addressable location in memory have the same unit, has a unique physically wired in addressing again mechanism, etc. So let's wait for a few seconds if any question. Okay, so now when it comes to, as we said earlier, from the whole characteristics of a memory system, now we have 3 major performance parameters that we use. And the 3 here is about the memory character. So first is the access time, how long it takes to access, that's the latency. let's say, CPU to access data from, CPU to access data from main memory or cache, which one have the low or high latency. Our goal is to lower it because it's time, how long it takes to access. Yeah. Also, we have the memory cycle time and then the transfer rate. So wait for a few seconds if everything is okay. We need to explain more. Okay, so let's keep going. So the main goal here, again, as we said, the two most important characteristics of memory is the capacity and performance. And the performance means how long the access time to access latency, or the memory cycle time, or the transfer rate, the bandwidth. So as we mentioned earlier, it's like we are repeating from the pyramid. The faster memory, of course, more expensive, and they have smaller capacity, such as register. Then the smaller memory, cheaper, larger capacity, including your hard drive, VHS, etc. Now, the hierarchy goal is to balance, again, the cost and the speed of access time. So wait a few seconds. So once we go through the concept of, again, cache, but as we said, we will go more detail on cache. We talk about cache hit and miss, etc. in our, again, next lectures. Which is, when I say next lecture, I mean next chapter. The next lecture, next chapter. Yeah, so that's cache. Cache also, I would say that actually says said over there, it's a small and fast memory, also close to the CPU. In terms of with the main memory, the CPU. Again, this is faster, cache is faster. But of course, cache is slower than register. And cache is bigger than, the capacity bigger than register. And the main goal of a cache, as we said, to solve Van Neumann bottleneck, is to reduce the average memory access time by storing frequently used data. There's algorithm for the concept of mapping the data from RAM to cache. Also, second item exploits temporal and spatial locality. And cache also have different levels. Here we have 3 levels, level 1, 2, and 3. Level 1 is the closest, but it will be the smallest also. Then we have level 2. Level 2 is bigger, but it's slower than L1, level 1. So we are assuming level 1 is the closest to the CPU. Then we should understand the concept of cache hit. In short, this will be data that is found in cache. Then cache means, in short, will be data not found. So this must be fetched from lower, again, memory levels. So I think that's all we can say here. Let me wait for a few seconds. Maybe time to take a short break now. Let's look at our time. Okay, we have 3:10, so I think we almost 1 hour 40 minutes. Well, because of the quiz, but it's about time to take a break now. So let's wait for a few seconds up to here. As we say, Cache is a chapter by itself, so we may go more details on it. Hopefully, if not today, next week. That will be the next chapter. Okay, so it's like there's no question. Let me pause my recording first. There's no stop.